Now it's time to apply what we have learned about the LoRa technology into a real simple project. But before we start talking about a real LoRa module and use it in a simple project, let's talk about the manufacturer of the LoRa chip used in this workshop, Rayax. Rayax is a Taiwanese company founded in 2008, has become a leader in IoT by empowering companies to develop connected devices. Their core strength is designing high-performance wireless modules, the communication heart of what is called things like Bluetooth speakers and smart sensors. This variety ensures compatibility across applications, but Rayax goes beyond hardware. They partner with companies through engineering design services, ensuring their modules integrate seamlessly. They understand the challenge of sourcing IoT parts and offer supply chain management to streamline the process. So Rayax is a one-stop shop for IoT. They provide the tools, expertise, and support to navigate the complexities of this industry. Visit their website on www.rayax.com. If you want to download the documents of the Rayax LoRa module RYLR998, go to Products, LoRa, choose the version from here, and just download the from this download section, download the datasheet and the AT command in English. The Rayax RYLR998 LoRa transceiver module is designed to provide long-range spread-spectrum communication with high interference immunity and low power consumption. Some key features of the RYLR998 version. First, it's the Novoton, a microcontroller unit, and Semtech LoRa engine. This combination of microprocessor and LoRa engine enables the module to achieve the long-range communication. LoRa technology is specifically designed for low-power, long-range communication, making it ideal for applications such as remote monitoring and industrial automation. Excellent blocking immunity. This feature helps to ensure that the module can function properly even in environments with a lot of electrical noise. This is important for industrial applications where there may be a lot of electrical equipment that can generate interference. Smart receiving, power saving mode. This mode helps to conserve battery life by reducing the amount of power that the module consumes when it's not receiving data, when it's in the sleep mode. This is especially important for battery-powered applications where extending battery life is very important. High sensitivity. This feature allows the module to receive signals from long distances even in weak signal conditions. This is important for applications where the module may be located in a remote area with poor signal strength. Control easily by AT commands. AT commands are a type of command set that is commonly used to configure and control electronic devices. The fact that the RYLR998 LoRa module from Rayax can be controlled by AT commands make it easy to integrate into a variety of applications. This simplifies the development process for us. The built-in antenna eliminates the need for an external antenna, which can simplify the design of your project. This can save space and reduce complexity in applications where size and weight are important considerations. Command support data encryption. This feature helps to protect your data from being intercepted by unauthorized devices. This is important for applications where sensitive data is being transmitted, such as industrial control systems or remote monitoring applications. Overall, the RY-LR998 LoRa module is suitable for a wide range of applications, from smart agriculture and smart cities to industrial automation and remote tracking. Its long-range communication, low power consumption, and ease of use make it a valuable tool for engineers and IoT developers. The pin description of the LoRa module. This is the shape of the LoRa module. It takes the shape of a bird. It has 5 pins. The right pin is the VDD. This pin supplies power to the module. The recommended voltage level for this module is 3.3 volt. On the left, there is the ground pin. It's connected to the ground of the whole circuit. And next to the VDD, there is the reset. This reset pin is used to restart the module. It's often tied to a button or another logic pin that can be pulled low to trigger a reset. The RX pin receives data and instructions from the microcontroller and should be connected to the TX of the microcontroller, and the other UART pin, the TX, transmits data from the module and should be connected to the RX of the microcontroller. So we need to connect the VDD to the 3.3 volt, the ground to the ground, and we need to connect both the UART data input and which is the RX, and UART data output, the TX, to the opposite pins in the microcontroller. You can ignore the reset pin. Let's move on. This is the timing diagram and the block diagram. Now let's take a look at the datasheet of this module to get more specific information about its technical specifications. The RAYAX RY-LR998 module operates on a power supply ranging from 2.3 volts minimum to 3.6 volt as maximum, but the typical power is 3.3 volt. The RF output power, which refers to the strength of the signal transmitted by the module, can be set from 0 to 22 dBm. The datasheet cautions for the CE certification compliance, the output power needs to be set to less than 14 dBm. Higher output power allows for greater transmission range, but also consumes more battery power. The module receives sensitivity of -129 dBm, indicates its ability to detect weak signals. The lower this dBm value, or more negative, the better the sensitivity. In simpler terms, the RY-LR998 can pick up on faint LoRa signals. This is essential for reliable long-range communication. The module has a sleep mode rate of 10 microampere, ideal for battery-powered applications. The baud rate can be set from 300 to 115-200 bit per second, which is the default. It operates in the 820 to 960 MHz frequency range depending on the version, and it has a frequency accuracy of 10 parts per million. The flash data memory has a cycling endurance of 200,000 cycles. The weight of the module is 1.83 grams and the operating temperature range is -40 to 85 degrees Celsius, which is a very good range to operate in any weather condition. Alright, now let's start deal with the RYLR998 module using the AT command guide. AT commands are a type of instruction that you can send to a device to control its behavior. In the case of the RAYAX modules, AT commands are used to configure the LoRa network settings and to send and receive data. You can download this guide from the RAYAX website www.rayax.com. In order to use this LoRa module, we need to configure it to use it for the first time. To configure the LoRa module, you need a USB UART or USB TTL adapter like this. Connect the LoRa module with the adapter and the adapter with the computer. Just connect the 3.3 volt of this adapter with the VDD of the LoRa module and connect the ground here with the ground with the LoRa module. Connect the TX pin here with the RX pin on the LoRa module and connect the RX here with the TX on the LoRa module. Then connect that to a USB on your PC and open the Arduino IDE. Select Tools, Port, and choose the port of the USB you have plugged in and open the serial monitor. When you type AT, if you got an OK like this, so it's now ready to start configuring it. But if you have any errors, go back and check your connections. Alright, back to the command guide. There's a sequence to configure and use the AT command. First, we need to use the AT plus address to set the address. Setting the address of the transmitter or the receiver of the LoRa module you are going to use. You can go back to see further explanation about this command AT plus address. You can set it from 0 to 65535, but the default is 0. You can check the address of the LoRa module you use right now by just typing AT plus address. I have set an address before, so it's the address of this module is 10. Yes, it's 10. You can set any address you want by typing AT plus address equal to whatever the address you want to set, like 100. Okay, if you check it again, it will be 100, but I will set it to 10 again because I have used this address in the project we're gonna build. Alright, the next sequence is setting the network ID. Setting the ID of the LoRa network allows the device on the same network to communicate with each other. If the network ID of the transmitter and the receiver are different, they will not be able to communicate with each other. So they will need to be on the same network ID. You can set the network ID. You can check the default value first by typing AT plus network ID ? It's 18. You can change it AT plus network ID equal to, there is a range. You can go to the explanation of this. You can set it from 3 to 15 or 18. I will keep it as it is, 18. Next is the band, the frequency band. It sets the center frequency of the wireless band the module will use for communication. Value also should be the same for the transmitter and the receiver. They are required to use the same frequency to communicate with each other, so they need to be on the same network ID and have the same frequency band. Let's check the frequency band of this module by typing AT plus band question mark. It's 915 and 6 zeros. This is the frequency band of my region. You can check the frequency band of your region and type it. Next, the parameters. We need to set the RF wireless parameters. The function of this command is to set the various radio frequency parameters that affect data transmission. These parameters include the spreading factor, which we covered all those parameters previously, explained them briefly. The spreading factor controls the trade-offs between range and data rate. Higher spreading factors offers longer range but slower data transmission. We also set the bandwidth. The smaller the bandwidth, the better the sensitivity, but the transmission time will take longer. The coding rate controls the amount of error correction added to the data. Higher coding rate increase error correction but reduce data rate. The fifth parameter is the preamble code. It's a shorter sequence of bits used for synchronization before data transmission. Here is an example of how to set the parameters of the LoRa module. First is the spreading factor. You can choose from SF7 to SF9 at 120 kHz bandwidth, or SF7 to SF10 if you choose 250 kHz, or from SF7 to SF11 if you set the bandwidth to 500 kHz. So the AT plus parameter is equal to first the spreading factor, whether it's SF7, SF8, SF9 and so on, comma the bandwidth. You can choose, if you type 7 in the bandwidth here, it will be the default, which is 125 kHz. If you typed 8, it will be 250. If you type 9, it will be 500 kHz. Comma the coding rate, which can be from 1 to 4, the default is 1, and finally the programmed preamble. The default of it is 12. When the network ID is set to 18, the value can be configured to 4 to 24. Other network ID, if you use any network ID other than 18, you should set the programmed preamble to 12. So you type AT plus parameter, type first the spreading factor, comma bandwidth, comma coding rate, comma the programmed preamble. Let's check the current parameters of this module. Parameter question mark 794 and 15. You can change it to whatever you want. Parameter equal to 7 or 8, 8 for 12. Okay, you can check it back. Let's get it back to the previous value, 7, 9, 4, 15. Okay, great. Now we have set the LoRa module successfully. If we want to send data to other LoRa module again on the same network ID and on the same frequency band, you just type AT plus send equal to, first you type the address of the LoRa module you want to send this data to, comma, type the number of characters of the data you will send. For example, I will send the hello word, which consists of 5 characters, so type 5, then type the message hello and click send. Okay, if you set the other LoRa module successfully and open its serial monitor beside this, you will receive the message. We will see all this in the upcoming project. Now the project time. In this project, we will build a simple system that takes the temperature and humidity of an environment and send it using LoRa module to another LoRa module and display it on LCD. This project used 2 microcontrollers, ESP8266 and ESP32. The ESP8266, this microcontroller is responsible for collecting temperature and humidity readings from an DHT sensor. The DHT sensor uses a single data pin to send digital signals representing the temperature and humidity. These signals are then transmitted wirelessly to the ESP32 using the LoRa module. The LoRa modules function as transceivers, enabling wireless communication between the 2 microcontrollers. They use LoRa technology known for its long range and low power consumption. The ESP32 receives the temperature and humidity data from the ESP8266 via the LoRa module, and we will use a I2C LCD to display the received data. The I2C is a serial communication protocol commonly used for connecting low-speed peripherals to microcontrollers. So, in summary, this circuit design showcases a wireless data transmission system between 2 microcontrollers using the LoRa technology. The components: an ESP8266 and ESP32, and I have a special edition of this ESP32 from ASWA, may be different from the one you have, so download the datasheet of the one you have as shown in your datasheet. We will need 2 LoRa modules, RAYAX RYLR998 or equivalent, 1 DHT11 sensor, LCD that supports I2C communication, jumper wires, breadboard, and with power supply, and of course an Arduino IDE and the laptop. Here's the schematic of the circuit. On the left there is the transmitter circuit, and on the right there is the receiver circuit. You will need to provide a stable power supply for each ESP microcontroller. Individual voltage regulators are recommended for better control and isolation. Alternatively, a common LiPo battery can be used with dedicated voltage regulators modules. To provide 5-volt power supply to each ESP, connect the ground pin of each power supply to the ground pin of the respective ESP. This will establish a common ground reference for all components. On the transmitter part, we have a LoRa module and the DHT11 sensor. For the LoRa module, connect the VDD to the 3.3 volt pin on the ESP8266 and connect the ground here on any ground pin on your ESP. Connect the RX on the LoRa module to the TX on the ESP and connect the TX on the LoRa with the RX of the ESP. The DHT sensor have 3 pins. The first one is the VDD connected to 5 volt or 3.3 volt, the ground to any ground pin on the ESP, and the digital pin on the DHT sensor connected to any GPIO pin on your ESP. For the receiver part, do the same for the LoRa module, and to connect this LCD that supports I2C connection, you will find 4 pins on this LCD: SCL, SDA, VCC, and the ground. SCL connected to the SCL pin on your ESP32. Just open your datasheet and locate the pin that supports the serial clock or SCL. Connect the SDA with the SDA on the ESP, the VCC with 5 volt pin on your ESP32, and the ground with the ground. Now let's take a look at the code. This is the transmitter code. First, we include the libraries. The software serial library enables us to create a software serial port on the microcontroller. This allows communication on pins other than the hardware serial pins. The DHT library provides functions to interface with DHT series sensors, allowing us to read temperature and humidity data. Next, we define some constants for the DHT sensor. The DHT pin defines the pin number to which the DHT sensor is connected. The digital pin of the DHT is connected to the digital pin on the 5 on the ESP. The DHT type is DHT11. Next, we create an instance or object of the DHT class named DHT, which represents our DHT sensor. We pass the pin number and the type of the sensor we have. Next, we declare some variables. The previous milli stores the time in milliseconds when the last data transmission occurred. Interval specifies the time interval between consecutive data transmissions. We set it to 3000 milliseconds or 3 seconds. Here we create a software serial port named REAX LoRa using pins 13 as RX and pin 15 as TX. The setup function, we perform the initial setup tasks like initializing the DHT sensor using the DHT.begin function. Start the serial communication with the default baud rate 9600. This is the hardware serial port between the microcontroller and the laptop, and we initialize the software serial communication between the microcontroller and the LoRa module, also at the same baud rate 9600. Make sure that you change the default baud rate on the LoRa module using the USB TTL adapter using the command AT plus IPR equal 9600, because the default value of the RYLR998 version is 115200. But what are those hardware and software serial communication? The hardware serial communication is a feature provided by microcontrollers where dedicated hardware modules handle the transmission and receiving serial data. This hardware-based communication is more reliable and efficient than software serial communication. It's typically used for communication with peripherals like USB, Bluetooth modules, GPS, and other microcontrollers. In this code and in the receiver code, the hardware serial communication is initialized using the serial.begin function. This function sets up the baud rate for serial communication and initialize the hardware UART module of the ESP we have. The baud rate determines the speed at which data is transmitted and received over the serial port. Hardware serial communication typically use specific pins on the microcontroller designed for serial communication, known as RX and TX. The pins are connected and included in the USB that you plug into your PC. This USB allows the serial communication and enable us to open the serial monitor to see and debug the code. On the other hand, the software serial communication is a method of emulating serial communication using software libraries on microcontrollers. It allows serial communication on any digital pin of the microcontroller. This enables us to communicate with devices that require serial communication but cannot use hardware serial ports due to limitations like the number of hardware UARTs available or maybe conflicts with other peripherals. In this code, the software serial communication is used for communication with the LoRa module using the software serial library. This library enables the creation of a virtual serial port named RAX LoRa on specified digital pins 13 for RX and 15 for TX. The software serial.begin or rax.lora.begin initialize the software serial port with the specified baud rate similar to the serial.begin here. The software serial communication is often used in DIY project or simple project when additional serial communication ports are required beyond the hardware UART available in the microcontroller. In summary, hardware serial communication offers higher reliability and efficiency, but it's limited by the number of hardware UARTs available, while software serial communication provides flexibility in choosing communication pins but may have limitations in speed and reliability, especially at higher baud rates or when handling multiple serial connections simultaneously. Finally, we add a small delay of 100 milliseconds for stability. In the loop function, we continuously execute this code. First, we get the current running time of the microcontroller using this millis function, and we store it in current millis. We check if the elapsed time since the last data transmission or previous mils is greater than or equal to the defined interval. If yes, we proceed with sending data and record and store the current time to the previous time variable. Next, we define the address of the LoRa module that will receive the data. We read the temperature and humidity data from the DHT sensor. Then we construct the sending command that we have seen before on the AT command guide we store the command we will send in a variable called sending data. This is a string variable. First we type 80 plus send plus equal to 10. 10 is the address of the microcontroller. Sorry, there is a mistake here. That 11, this 11 is the number of characters that will be sent. So this is the num of characters, and 10 here is the address of the LoRa module that will receive the data. We add comma to the message and send the number of characters, comma, string of the temperature. The temperature that the DHT produce is a float number, but we will need to send it as a string, comma, string of the humidity reading, and we end the line. We will send this message using reax LoRa.print, and finally we print it on the serial monitor for debugging purposes and wait for the data to be transmitted using serial.flash. Finally, we check if there is any response available from the LoRa module. If there is, we print it on the serial monitor. Now let's upload this code to the ESP8266 microcontroller. Just connect the USB and choose the port. Make sure that you choose the type of the board here. Choose the port and click upload. Done uploading. Now let's open the serial monitor to see what the data is being sent. As you can see, here is the data. 80 plus send is equal to, this is the address, number of characters, those are the characters, you can count them and you find them, 11 characters, including the comma and dots here. And we receive the OK message from the LoRa module. Now let's see the code of the receiver port. The receiver code, we have two libraries. We have included the software serial library and the liquid crystal I2C library is included also to facilitate the communication with the LCD screen using the I2C protocol. This line initializes an object named LCD of the liquid crystal I2C class. It specifies the I2C address of the LCD module. The address is 0x27, and this address may be different depending on the chip on your LCD. Just search on YouTube how to find the exact address of the I2C of the LCD you have. This line declares a global string variable named received data. It's used to store the data received from the LoRa module. This line creates a software serial port named reax LoRa, just like the transmitter port, using pin 16 as RX and pin 17 as TX on the ESP32. The software serial port is used to communicate with the LoRa module. The setup function is called once when the Arduino starts. It initializes serial communication for debugging with the default baud rate 9600 using serial.begin. It also initializes software serial communication with the LoRa module at the same baud rate. The LCD is initialized using this line. We clear it, then we turn on the backlight. Memory is reserved for the received data string to prevent dynamic memory allocation during program execution, which can lead to memory fragmentation and instability. Finally, we add a delay of 100 milliseconds for stability. The loop function runs continuously after the setup function. It checks if there is data available to read from the LoRa module using LoRa-based function. If yes, if there is data available, it reads the string using reax_LoRa.readString and save it to the variable received data. The getValue function is then used to extract specific values, the address, the temperature, and the humidity from the received string. This function splits the string based on a delimiter, which is comma in this case, and store the value at this variable. The extracted values are displayed on the LCD using lcd.print. We print the temperature, temp, and the temperature and Celsius, and we print the humidity also as a percentage. The extract values are printed on the serial monitor for debugging using serial.print. Finally, the serial.flash ensures that all the data is transmitted before continuing. Let's upload this code to the ESP32, the receiver. Make sure that you choose the type of your board, which is ESP32 dev module, and choose the COM port, which is COM6, because the COM4 is the transmitter, and click upload. Done uploading. This is the transmitter circuit. This is the ESP8266, the DHT sensor, and this is the LoRa that sends the data to this LoRa module. This LoRa module will take the data and send it to the ESP32 microcontroller, and this ESP32 microcontroller will process the data and display it on this LCD. As you can see here, the temperature is 24.8, the humidity is 59%. Here is the data that are being sent from the transmitter. As you can see, the temperature 24.8 and the humidity is 59 as here on the LCD.